Hi, this is Chol, and I'm here for my final presentation. I am researching security solution for CAN-bus communication. I titled this with CAN-bus communication, but I hope this can be a solution for any multi-broadcasting communication systems. This topic is Dr. Kim's idea, and I'm very thankful that I have a chance to contribute to it. The next page. So what is CAN-bus? Canvas is a control area network system. It is a robust vehicle bus standard designed to allow microcontroller and device to communicate with each other's application without a host computer. It is a message-based protocol designed originally for multiplex electronical wiring with automobile to save on copper, but can also be used in many other contexts. For each device, the data in the frame is transmitted sequentially, but in such a way that if more than one device transmitted at the same time, the highest priority device is able to continue while the others back off. So basically, those ECU communications with each other through this CAN low, CAN high copper. And also there is one other important thing, the ECU has very weak computing power. Page, current campus data frame. Let's see what the message structure looks like in current campus system. So there is SOF, which is start of frame, which is indicate the beginning of the message, and CAN ID or extended identifier, the CAN message identifier and its property, RTR, the remote transmission request, allows which allows the system to request the message. And control is indicate the length of data to be transmitted. And data is containing the information value. And CRC, the cyclic redundancy check, is result of a calculation based on the number of transmitted information. It allows the detection of transmission errors. And ACT, if you took the network class, you easily know what it is. It's acknowledge. It is when the message is successfully transmitted to the receptor, the acknowledge informs the emitters. Okay, and the EUF is just end of frame. Okay, next page. However, this research proposed a new data frame structure. Data field is the same as the current campus data structure. New parts are receiver, sender, sequence number, and MAC or HMAC. Receiver is as it is, the data receiving ECU. The sender is the message sender ECU. The sequence number is the message number, simply it is the counter value. And this is very important because this will be the tool to detect replay attack and will be a source for driving key for encryption. MAC or HMAC is hashed or message authentication code. In this research, we will encrypt the data part and signature for all other parts. So how to construct more secure communication in Canvas system? To make this system more secure, this research proposed that Canvas communication needs authentication and encryption. Therefore, this research implements ECDSA for authentication and AES for encryption with CBC mode. And this is about authentication. And I use ECDH for key exchange and ECDSA for digital signature. I assume you guys know ECDH, which is elliptic curve Diffie-Hellman, and ECDSA is elliptic curve DSA. So yeah, because we went over this a lot in our class, so I'm going to explain this briefly. To create the key, we need to select the random integer d in the interval 1 to n-1 and compute q equals d times g, and declare that q is the public key and keep d as a private key. This is how we sign for the message And inputs are message digest HM, which is hashed message. And in this research, I select the SHA-1 hash function to hashing the message, and private key D and R and K, which are random number. R should not be 0, and if all is 0, create new random number K. After creating R successfully, S will be calculated with line number 4, which is you can see right here. So S equal K minus 1, this part. And also, S should not be 0. If S is 0, to create new random number K and repeat it. This is how to verify signature. Similar as signing, we need a message digest HM, which is hashed message, and public key XY, and R and S, and base point G. After those calculations, if X2 and R are same, then it is successfully passed the verification. If you want to leave more detail in this ECDSA authentications, like creating key, create key, like calculating signature and verifying signature, more detail, you can see Dr. Kim's lecture slide on September 22nd and page 21 to 23 clearly explain how it works. We are in the cryptography part. In this project, we will use a symmetric key, and every ECU will have a table for key which will look like those table on the right. For example, so there's ECU1, ECU2, they all have the public keys, but there's none here and none here because these parts are shared key, and ECU1 and ECU1, obviously they are same ECU, they will not send a message and receive a message for themselves, so they doesn't need the shared key. And same as ECU2 here, they doesn't need shared key for same ECU, so it's none, but the other, they all have one. Okay, next slide. This project, we use AES, CBC mode encryption. I assume we all know what is AES because we goes over AES in our class, but let me go over it real quick. AES is Advanced Encryption Standard System, and the algorithm were all to be block cipher, supporting block size 128 bits and key size of 128, 192, or 256 bit. As we all know, block cipher is not perfect because the same input and same key will produce the same output. In this project, we choose CBC mode because it is good for bulk data encryption. Also, message blocks are linked together. Each previous cipher block is chained with the current plaintext block. A change in a message affects all ciphertext blocks after the change, and also uses initial vector IB to start project. And IB is a random number generated by sender and sent together with the ciphertext. We all know a one-time pad is the best one. Also, reusing old key is very harmful. You guys remember this figure? This figure shows how harmful to using old key again and again. In this research, we do not using symmetric key itself in the table. The shared key in the table. We derive the new key with PBKDF2 algorithm. PBKDF2 algorithm means password-based key derivation function 2. And it is obviously key derivation function with the sliding computational cost used to reduce vulnerability to brute force attack. PBKDF2 applies pseudo-random function such as hash-based message authentication code like HMAC to the input, password or passphrase along with the sort value and repeat the process many times to produce a derived key, which can then be used as a cryptographic key in subsequent operation. The added computational work makes password cracking much more difficult and is known as the key stretching. And you can see here this diagram, and this is like simple diagram to explain PBKDF2, but let me explain this function code. So PRF is pseudo random function of two parameters with output length h-lang, and password is the master password from which a derived key is generated, and salt is a sequence of bits known as cryptographic salt, and C is the number of iterations desired, and dk-lang is the desired bit length of the derived key, and dk is obviously the generated derived key. And this project, the salt will be the sequence number in our new proposed Canvas data frame. So our sequence number will not be never same, because each time we generate a message, even if the data is same, so even if the message is same, our sequence number is always different. So therefore, our key will be never be same. So where are we going to store our all keys, the tables? So TPM is where we store key tables. And first, thank you and credit to Binay, who was the master student under Dr. Kim, and I learned this detail from his paper. However, the TPM is known as Trust Platform Module. It's an international standard for secure microcontroller that protects hardware using integrated cryptographic keys. TPM typically provides the following functions. First, random number generator. Second, generation of locking, unlocking of cryptographic keys. And third, full disk encryption. Therefore, in this research, proposed that each ECUs are connected with their own TPM, so we can generate and store and use keys very secure way. So we are successfully implementing an encryption and verification system with Python test code. So why did we do it? Because obviously it is way safer for many attacks. For example, modification attack, it will fail in our authentication system because it changes the data. Fabrication attack is also failed in authentication because the data is different also. And replay attack can be detected by checking sections number. A replay attack, as known as playback attack, is a form of the network attack in which valid data transmission is maliciously or fraudulently repeated. So we had the sequence number before in our proposed data structure. So even if it passed authentication and decryption, we can easily know there is the replay. Because even if they pass it, the sequence number must be same because it's a replayed attack, but we cannot have any same sequence number. So if we know sequence number beforehand, and we compare it, so is there a sequence number before or not? So if it's the same sequence number that's stored before, then it is obviously the replay attack. Thank you for hearing my presentation, and yeah, obviously this is the recorded presentation. So if you have any question, concern, or suggestions, please email me under that email address. Thank you again, and happy Thanksgiving. Bye.